Hello, welcome to my presentation. My name is Michael Schlatt from the University of Louisville Distributed System Design course. Today we're going to be discussing the paper, Finding a Needle in Haystack, Facebook's Photo Storage. During this presentation, we're going to follow along the 2010 paper from Facebook, where we're going to provide a little bit of introduction to the Haystack platform, give a little bit of a background, motivation, and previous design, which led to the requirements for Haystack, go over the design and the implementation of that design, followed by the evaluation of Haystack, and then finally conclude with related work and conclusions. As you probably guessed by now, this paper talks about Facebook's Haystack, which is an object store platform which they specifically designed to optimize for photo storage and retrieval, which is by far the most popular feature on the social media platform. Back in 2010, when this paper was released, there were 260 billion images on the site. At this point in time, that number has to be exponentially larger. At that time, they were getting about a billion per week uploaded, and that accounted for about 60 terabytes. This does take into consideration that for every photo that is uploaded to the platform, they actually store it in 4 different sizes. What they found was that traditional design incurs way too many costly disk operations. So this is anytime that you have to do an I/O operation to get metadata, file information, actually read from the system, lock the file system, anything like that. Anytime that you have to interact with these disks, it's a pretty costly operation. So their solution, or their idea, was that they wanted to reduce the amount of metadata that they had to process and then perform pretty much all of their lookups in main memory, as opposed to having to actually go back out and touch the disk. This led to the engineers coming up with 4 main requirements for the Haystack platform. One, it had to have high throughput and low latency. This makes a lot of sense just based on the nature of what Facebook is doing. They're receiving many requests from all around the world, and they need to be fulfilled quickly with the lowest possible latency to give the users a good experience. And they also wanted to reduce their dependency on their costly content delivery network, which is essentially a giant cache that they pay somebody else to help them out with. And that was proving to be pretty costly for them. They needed the system to be fault tolerant. I mean, any internet scale system at this point in time, had to expect failures. They're going to be normal, and it has to be able to recover from that very quickly. Facebook is a commercial enterprise. They are a for-profit company. This is not scientific research or anything like that. So cost effectiveness is definitely a primary motivator for any project, at Facebook. And finally, the requirement it had to be simple, and not just because simple is better. It really had to do with the fact that this solution was being delivered straight to production, and they really wanted to minimize the amount of testing and integration errors that they were going to occur, deploying a new system. And so the best way to do that was to keep the system as stripped down and simple as they possibly could. To understand why Facebook wanted to create their own object store system to begin with, let's take a look at their previous design that they were using and go over some of the pitfalls for that. So figure 2 here shows a solution that they utilized that was basically an NFS solution, or network file share solution. And in this picture, you can see that there are NAS devices directly connected to a photo store server. And the communication flow would work something like this. Your browser would go out to the web server, say, hey, what do I need to pull down this website to display to the user? The web server would respond with a list of resources that it needed to get. In this particular example, it's going to be a photo. And so once the browser has a URL or a location of where that photo is stored, it reaches out to the content delivery network. If the content delivery network has that resource or photo cached, it'll immediately return it. But in this scenario, it's not cached, and it needs to go out to the photo server. And the photo server then communicates with a NAS device, and the NAS device simply retrieves it. What the engineers found was that the content delivery networks by themselves are not optimized for social media photo storage. And they are highly effective of storing and caching the most popular content right away, so they don't actually have to make those additional steps to go out to the photo store server and the NAS devices. But what Facebook has and other social media sites have is a problem with what they call the long tail. And long tail are those requests that are not as popular. So if you're just going and looking at your aunt's or your grandmother's photos, that's very meaningful to you, but probably not a lot of other people are doing that. And so that's part of the long tail. A lot of folks are requesting content that really only they're interested in. And because of that, disk operations were unavoidable. So to address these issues associated with long tail requests, Facebook came up with the Haystack architecture. And the Haystack architecture consists of three core components: the Haystack store, the Haystack directory, and the Haystack cache. Figure 3 here shows the communication structure for a read operation. We'll go into this diagram a little bit more in detail in future slides. So the first core component is the Haystack directory. And the Haystack directory has four primary functions. The first one here listed is providing a mapping from logical volumes to physical volumes. Anytime that you have a distributed system like Haystack, you're going to have logical volumes that are mapped to one or more, usually more for replication purposes, physical volumes. It's a very important operation that is provided by the Haystack directory. Secondly, it balances both writes and reads, basically saying, which physical volumes should be utilized in any particular situation. It also determines CDN usage, and this can be manually dialed up or down depending on other needs of the network at the time, cost considerations, or anything like that. And finally, it identifies read-only volumes. One of the key functionalities of Haystack is they have a concept of read-only volumes and read-write volumes. Read-only volumes exist when a volume is full, and they also exist if there's any sort of operational errors that happen with them. And we'll discuss exactly what volumes are a little bit further. The Haystack cache functions as an internal CDN. And it's pretty similar to the external CDN, except for it's specific to the Haystack platform itself and operates a little bit differently. First of all, it can receive HTTP requests both from a CDN or a user's browser directly. And it is implemented as a distributed hash table, which is pretty common of these type of caching systems. But what separates it from a commercially available caching system, other than the fact that it is internal and they're not paying somebody else for it, is that it only caches a photo if both of these two criteria are met. First, the request has to come directly from a user, not the CDN, because why would it cache something that's already going to be cached, by the CDN itself? And secondly, the photo is only if the photo is fetched from what they call a write-enabled store machine. And the reason why they don't cache read-only store machines is that most photos are read, immediately after being written. Basically, you upload a photo and then it gets distributed out on people's news feeds, and so it's a lot more likely that a photo is read after it's been written. And they implemented this caching system to help reduce the burden on the machines that are handling the writes. So it kind of reduces the loads. They really needed the extra caching and the extra help on the write-enabled store machines. And this brings us to the most important, or at least the most unique part of Haystack Core, and that's the Haystack Store. And this is the devices that actually contain the disks that are going to store the photos. So each store machine handles multiple volumes. And what they call volumes are simply just really large files, files that are above 100 gigabytes each. And this is really a key component because storing many photos into a single file. In fact, each volume can contain millions of photos. What you do is you actually greatly reduce the amount of metadata that you have to have for each photo. And in order to store individual photos, they call them needles, and which makes sense because it has needles in a haystack. And needles are essentially sections of that file that represent a photo. And the photos are accessed quickly using a combination of the volume ID, the offset of that ID, where in the volume that file is located, and the size. And they are actually able to keep a mapping of photo IDs to metadata entirely in memory. So we'll take a look at what one of these needles looks like here. So on this slide, we have pretty much a layout of what a needle looks like. Each needle contains a header to basically identify that it's a needle. So that way, if you're scanning through the volume, you can reconstruct, you know, the files if you don't have the actual mappings. They have a cookie, which essentially is a nonce that they use to mitigate brute force lookups. There's a key and then an alternate key, and these are 64-bit and 32-bit IDs that uniquely identify each photo. There are flags. The flags really are only used to signify if a file has been deleted or a photo has been deleted, because one property of these volumes is that they never actually overwrite anything. They just keep on appending. And we've seen this in several other distributed file systems before. We have to know the size of the file, the actual data for the file, the footer that indicates that the data is basically done, and then we have a checksum and then the required amount of padding to properly align these files. So now that we have a brief overview of what each of the core components are, we can go over a simple read operation. So in this particular case, the browser is going to request from the web server a file that it wants to read. The web server is then going to consult the Haystack directory, and the Haystack directory is going to basically give that logical volume to physical volume mapping and perform some of the load balancing operations related to that. At that point, the browser has a choice depending on the configuration of the day, and the Haystack directory will tell the browser this, if it should reach out to the CDN or if it should go directly to the Haystack cache. Either way, in this example, we're going to assume that there's a miss, and if it's not found in the CDN, if it's not found in the cache, then the cache is then going to request it from the store. And a couple key points here is that the cache machine is going to supply a volume ID, alternate key, and cookie to the actual Haystack store. At that point, the store looks up the metadata in its in-memory mapping. It then pulls the volume, seeks to the offset, reads the photo. After it gets done reading the photo, it's going to then verify the cookie and the checksums before it returns the photo. A write operation is actually significantly simpler because we don't have to deal with the CDN and we don't have to deal with the caching system. Additionally, write operations can be performed asynchronously. So in this case, your browser is just going to reach out to the web server to say, hey, I want to upload some photos. The web server is then going to consult the Haystack directory, which again is going to provide that logical to physical volume mapping, as well as any load balancing operations that need to occur here. And at that point, the web server is going to be the one that reaches out to the Haystack store to initiate that upload and actual store. A couple notes here. Like I mentioned before, physical volumes are never overwritten, ever. They're only ever appended, so they keep on growing. It's very similar to a logging file system, which is referenced in some of the related works. Additionally, anytime a write occurs, the in-memory mappings also have to be updated, and that's handled on the store machines themselves. When we want to delete a file, because we never overwrite anything, we simply set the flag as deleted. Garbage collection is actually performed at a later step. In addition to the core components that we just covered, there are a couple other design and implementation details and features. This one that we want to talk about is what they call the index file. And the index file is used for optimizing the reboot and recovery process, and it does so by allowing the store machines to rebuild their in-memory mappings quickly. And essentially, it's a file that looks similar to what we have here in Figure 6, where you have information surrounding the needles kind of concatenated together into a single index file. And each one of the entries contains the important information that you would need for an in-memory mapping, including the key, the alternate keys, the flags, the offset, the size. And it's pretty straightforward to rebuild the memory mappings just by reading in this file. However, there are some complications that arise due to the asynchronous nature of the writes. And essentially what could happen if there happens to be a failure that occurs in between the time when a needle is created and when its entry in the index file is written, you're going to have basically what they call an orphan needle, or a needle that doesn't have, an index written for it. They're able to correct this by identifying the orphans and reconstructing the index mappings. And the way that they're able to quickly identify orphans is that the last needle written to the index file is going to be, is going to, guaranteed not to be an orphan. So any needles written um, to the data store after the last index needle was written are going to be orphans. Another implementation detail to go over is the actual underlying file system which the data blocks are written to. The Haystack distributed file system was actually meant to be overlaid on top of other file systems. And at the time of publication, Haystack utilized XFS file system. They could have used any other ones, but they chose XFS for a couple different reasons. First of all, the block maps that the XFS uses are small enough that several continuous files can be stored in memory. And that's obviously very advantageous because they don't want to have to do disk reads and writes to attain those block maps. Additionally, the XFS file system provides pre-allocation, which is going to reduce fragmentation, and fragmentation is always bad when you're trying to deal with speed and low latency. Recovery from failures, just like just about every other distributed file system that we've discovered here or talked about in this class, recovery is an absolute vital portion of that. They actually have two different systems that assist with this process. The first one is called Pitchfork, which is basically a background task that checks, the health via, remote connections. It does things like try to do different read tests, different write tests, see if there's network connectivity, and other various, background tasks that it can do to check the health. Anything that it finds that it deems to be unhealthy, it's going to mark it as read-only and then put it on the shelf basically for manual analysis later. The second operation they have is what they call a bulk sync operation, which is essentially when the entire volume gets restored from a replica. This is an incredibly costly and rarely occurring operation. According to the paper, this operation really only takes place a couple times each month. The last bit of design and implementation details that I want to discuss here are some of the optimizations that the engineers did with Haystacks. The first one is compaction, which is pretty similar to garbage collection. In fact, previously I referred to this as garbage collection. And this is where they reclaim space from deleted photos, although it's not quite the same as you might think. In compaction, what they actually have to do is they actually have to copy all of the needles from one volume to another before then they're able to free up the first volume. Obviously, they're not copying anything that's marked as deleted during that operation. The second optimization they do is they actually don't store the entire needle in the mapping. For example, the in-memory mapping does not actually need to have the flags. And that's because they can simply just set the offset value to 0 and omit the flag section entirely. They also omit the cookie mapping. And the reason why they do that is they check to make sure that the values are valid after they retrieve it. So the in-memory mapping doesn't actually need the cookies, and it doesn't actually need the flags. According to the documentation, that saves them about 20% of space in their memory when they're doing those mappings. The last optimization they do, and this is a little bit obvious, is batch uploads. And that's largely because it's a lot easier, or it's a lot more efficient anyways, to write large sequential writes instead of creating, random writes by writing, smaller files. So typically if you upload like an entire album to Facebook, that's going to be written to disk, all at once in a batch upload. Now that we've discussed some of the design and implementation details, we want to move on to the evaluation section of this paper, which the authors of the paper actually provided a pretty lengthy evaluation section with some pretty interesting insights. So the first thing that the authors of the paper did as part of their evaluation was to characterize the type of request that they get from their photo application. So on this slide, we have a couple different figures here. Figure 7 really shows what they mean when they talk about, the long tail request. So what we see here is we see that there's a sharp rise in requests for photos that are newly created, just a few days old. And pretty quickly, after a couple days, the number of requests that they receive for those photos, drastically drops. However, it never really goes down to zero, which is why we see that long tail approaching 100%, which that represents, the cumulative percentage of access requests. Table 3 just talks volumes and volumes of different type of photo traffic, on Facebook. We see that when this was published, they were getting about 120 million photos uploaded daily, which translates to about 1.44 billion photos actually written to Haystack. And the reason why that number is about 12 times more is because for each photo uploaded, they scale it to 4 different sizes. Actually, you see that in the next row there. And they also store it on 3 different replicas. As far as the photos viewed, we see it's about 100 billion, 80 to 100 billion there, with the majority of those photos being the small photo category. The last row there on that table talks about how many Haystack photos are read. And you see that number is actually about 10% of the overall photos viewed at 10 billion. And the reason behind that is that the CDN and the cache actually does a really good job of servicing, 90% of requests. And only about 10% of the requests actually make it to the Haystack store. The way that the authors decided to evaluate the Haystack directory component was by looking at the way that the directory distributes reads and writes across the Haystack store machines. So figure 8 here actually shows a test where multi-writes operations were stored on 9 different store machines. And what we see here is there's actually 9 different lines closely overlapping each other on that figure. And because they're clearly overlapping each other and there's not a whole lot of separation between the lines, that's an indicator that the distribution is being very equally distributed amongst those 9 machines, because it looks like they're each bearing about the same workload level. And in the same vein, they also tested the Haystack cache system. The metric they used for this particular system was a simple hit rate. And that's a common metric that you would see, when evaluating a caching system. Here, under the dates that they tested here, the hit rate was approximately 80%, more or less, depending on the time of day. And you also need to remember that caching only stores photos if it's on a write-enabled store machine. If you remember from a couple slides back, we saw that almost 90% of requests were handled by either the CDN or the cache. I want to point out here that this is not the overall hit rate between the two of them. This is the hit rate just for the Haystack cache, not including the CDN. So that's why those numbers don't quite line up if you're expecting to see those numbers line up. When it came time to actually evaluating the Haystack store as a core component of the system, the authors of the paper took a little bit more involved approach. Instead of looking at a single metric, they actually looked at a couple different metrics, including latency and throughput, both read and write operations. And they did this through 2 different testing mechanisms. They did it through a synthetic workload and a production workload. For both systems, the Haystack was deployed on commodity hardware. At the time, that was an Intel Xeon CPU with 48 gigs of RAM and 256 to 512 NVRAM, plus a 12 terabyte rated storage array. Those specs are still actually pretty impressive 12 years later. But we do consider that commodity hardware because it wasn't special built for this. There were 2 processes that the team created to do their synthetic testing. One was called Randomo, which is a program that basically performs random read testing, and they use that information to kind of make a baseline that they can compare their other testing to. The other program they created was called Haystack, which was a custom-built program to perform a couple different tests. And on the next slide, we're going to see the results of these. I just couldn't fit them all on one slide, but I want to kind of talk about the different tests that they created. The first one just does a straight up read on 64 kilobyte images on the store machine with 201 volumes. The second test does a test where 70% of the operations are reads on smaller images and 30% are on larger images. The next three tests, C, D, and E, include writes. So they're going to be purely write tests with 1, 4, and 16 groups images into a multi-write. Remember, with the bulk uploads, they actually gain more efficiency, and their results support that on the next page. Test F is where 98% of operations were reads and 2% are multi-writes, and G is 96% reads with 4% multi-writes, and those kind of mimic what they would see the type of request in the production environment. And so on this slide, we have the results of the test that we just previously discussed. A couple things to highlight here is that test A and B are both performing reads. Test B includes smaller images, which actually both improve the throughput as measured as images per second, and also the latency. The writes, which we anticipated as we went up from 1, 4, and 16 groupings, did increase the throughput quite significantly. So the bulk upload definitely had some optimization properties there. The average latency got higher, but you would expect that because we're dealing with more data at that point. The last two tests, F and G, where they kind of mix the reads and writes together, did have lower throughput, which makes sense because you're having to do read and write operations on the same store objects. And after they finished their testing using the synthetic workload, they went and looked at their actual production workload and came up with a couple of observations as well. These two figures here show a couple different things. First, they show that write-enabled boxes receive more requests, which makes sense. That makes perfect sense because it's write-enabled boxes indicate that someone just uploaded an image, and that image is probably going to be read back out fairly quickly after it's written. Another interesting observation, as more data is written, the volume of the photo increases, which causes the read rate to increase on that particular store. The latency of multi-writes are low and stable. We see that on the red line there at the bottom. It's very low. The writes are very low latency, and that's due to the asynchronous nature of how writes are actually performed. And read-only machines were also very stable because they had very predictable type of operations that were being performed. And the write-enabled machines are impacted by both the number of photos stored on them, the cache that's being used at the particular time, and the fact that there are immediate reads after the writes. And this does support the synthetic testing data as well. So that wraps up the evaluation section of the paper. Really all that was left was to talk about some of the related work. Some of these are papers that we had already discussed within this class. For example, the Ceph paper, they directly reference because that is another file system that is tackling the problem of how do you manage metadata. With that file system, they actually calculate the metadata instead of store it in memory, like they're trying to do here with Facebook. Obviously, the Google file system is one of the pivotal papers on distributed file systems, and it's referenced here. Additionally, they talk about log structured file systems and network attached secure disk. And that pretty much wraps up this presentation. Just as a conclusion, we learned that Haystack is an object storage system for Facebook photos. It is designed to focus on the long tail request operation, and it really does that by avoiding disk operations by storing many images into a single file, or what they called volume, to reduce the metadata, and then caching all the metadata in memory so that they have a mapping to quickly retrieve those files. And it is designed to be incrementally scalable and fault tolerant. This concludes the presentation. Thank you for watching.